Hello, welcome to the MIT Informatics Tournament Spring Invitational 2024. Congratulations for your performance. I know it's been a really hard contest, but I'm sure you guys all did really well. And even though there might be small errors here and there, I hope you had a really good experience. But without further ado, we'll have Albert here to present the solution to problem 1. Albert, yeah, no. Oh, Albert, yes. Yes.
All right. So we'll start off with problem 1. This is 3-step. You're given an expression in n variables, x1 through xn, and you're told that they will take values in the set 0, 1. So they're basically binary. And the expression consists of a bunch of terms xi times xj times xk, and sum together. So in the example, I don't remember exactly what it was, but something of the form. This x1, x2, x3, x1, x3, x4, plus x2, x3, x4. And our goal is to find values of x1 through xn that make the given expression odd. So an example of how we can do this, for this expression, we can set all of the xi to be 1. So then this first expression evaluates, or this first term evaluates to 1. The next one is also 1. And the last one is also 1, so the sum is 3, which is odd. So to do this more generally, let's first think about what happens if we have a clause that occurs false. So if in our expression we have xi, xj, xk, and then later down the line we have another xi, xj, xk, mathematically this can be rewritten as 2 times xi and xj, xk. And since these are integers, no matter what we set them to, the 2 will make them even, and therefore it won't affect the overall parity of the expression. So if any clause appears more than once, we can basically cancel out pairs. So we only care if a clause appears an even or odd number of times. So this is good enough to get the yes or no answer on the first subtask, where each term has distinct variables. As for construction, you might notice that any 2 clauses say xi, xj, xk, and xi, xj, and something different by letter, for example. If we set each of these variables to 1, then since we've canceled out all duplicates, we know that this is going to be the only clause that ends up being equal to 1, since every other clause will contain a variable that we haven't set, and we can set all the others to 0. So this gives a valid construction for the first subtask. Now, you might have noticed that in the second sample case, where the expression is x1, x2, x2, plus x1, x1, x2, this is an example of an expression where there's no duplicate clauses, but nonetheless, no matter what we set x1 and x2, this expression will always be even. And the observation to be made here is that if we have 2 of the same variable multiplied together, it turns out that since the xi are binary value, it's always true that their square is equal to just itself. So to cancel these out, we can remove the duplicate 2's inside the clause, as so, and over here, x1 and x1, this can be contracted to just x1. And our expression then becomes, again, a bunch of clauses with, a bunch of terms with distinct variable names inside them. So it's x1, x2 plus x1, x2, which is just 2 x1 and x2, and we know we can cancel out duplicate clauses. Now for construction, we could try to do the same thing, where we pick an arbitrary clause after canceling repeats and setting it all to 1. But an example of where this actually fails is, for instance, x1, x2, x3 plus x1, x1, x1. If we just blindly set this to all 1s, then we'll accidentally also set this to 1s, so it's actually insufficient. So to amend our approach, after canceling this out to just a clause of a single variable, we can then find the clause with the smallest number of distinct variables and set that to 1. So every variable that appears in the smallest clause, we will make it 1, And since no other clause can then all be set to 1, as is the smallest clause, we are done. We have a construction for both cases. So that concludes the review for problem 1. Next we have problem 2, which is Marksman, presented by Benson.
Hello, I'm Benson. I'm the problem setter for problem 2 Marksman. I'll briefly go through the statement again. You have n lanes, and each lane may have 0 or more targets in the lane. So, for example, we can n equals 1, and we have one lane with one target. So we can imagine lane 1 contains a single target. So we want to shoot down all the targets in the lanes with the quirk that every second shot, so every even number shot, will hit the second target in the lane. So imagine if we only have one target in the first lane, we can shoot this target and we are done. But if we have instead two targets in the first lane, what will happen is that our first shot will hit the first target, and our second shot will never actually hit this target because we only have one target left in the lane. The second shot will miss because it will hit the second target in the lane. Now imagine that we have n equals to 2, we have two lanes with one more target in the second lane. Now this is possible because what we can do is we can shoot the first target in the second lane, the second target in the first lane, and the first target in the first lane. So with these small cases, we actually can come up with a number of important observations. So the first observation is that n needs to be odd. The reason for n being odd is that if n is an even number, it means that our very last shot will actually hit the second target of its lane. But you can imagine that at the very end, when we only have a single target left, we must shoot the first target in the lane. So if n is even, we cannot shoot down all the targets. So that is not the only condition though. If we create another example with n equals to 4, and we have 3 more lanes, we run into a separate issue. Now imagine we have this set of targets in 4 lanes. The first lane has 2 targets, the remaining lanes have 1 target each. Imagine if we shoot the first target in lane 4, the second target in lane 1, the first target in lane 3, and oops, we can't actually shoot any more targets because now all lanes that have at least 1 target only have 1 target remaining. And our fourth shot must hit the second target of a lane. In some sense, this tells us that we don't have enough lanes with more than 1 target to actually shoot. Which brings us to the second condition that we must check, which is that if we have n equals to 2k plus 1, we need to have at most k plus 1 non-empty lanes. A more rigorous explanation of this condition would be if we have 2k plus 1 shots. We can split this into k plus 1 first target shots and k second target shots. And because we only have k plus 1 first target shots, whenever we clear a lane, that last target that we clear must be a first target shot. So if we have more than k plus 1 non-empty lanes in total, we can't actually clear all of the lanes. With that, we have 2 conditions which will tell us whether we can actually shoot down all the targets across all of the lanes. And it turns out that these 2 conditions, while they are necessary, are also sufficient. We only need these 2 conditions to know whether we can shoot all the targets in the lane, in n lanes. So a very brief outline of the proof is that if you can imagine, if we have lots of lanes with lots of targets, alright, for example, if we have 2 lanes with 5 targets, we can just shoot any 2, and we can end up with fewer targets. But once we have exactly k plus 1 non-empty lanes and 2k plus 1 targets, we need to be a bit more careful. So what we can do is that once we have exactly k plus 1 non-empty lanes and 2k plus 1 targets, there exists one lane with a single target and exists at least one other lane with at least 2 targets, possibly more. We don't really care how many they are. We can reduce the number of lanes by 1 by first shooting the lane with 1 target and then the second target in a different lane that has at least 2 targets. This reduces the number of non-empty lanes by 1 and the number of targets in total by 2. So you can think of it as we are getting downwards. We can show that this will eventually shoot all targets in all lanes. So this gives us a way of constructing for given n and the number of targets, how to shoot all the targets in all the lanes. If you were to naively go through all of the lanes over and over again to find 2 such targets, you will actually TLE on the large test data because n is up to 300k. So to make this more efficient, you can think of it as we don't really care which lanes we are shooting. All we need to care about is that we're shooting one lane with 1 target and another lane with more than equal to 2 targets. So we can maintain 2 lists, one containing the lanes with only 1 target and the other containing the lanes with more than equal to 2 targets. We go through each of these lanes and shoot each of them one by one, and we look at the possible lanes with more than equal to 2 targets that we can match them. And once the lanes that have more than equal to 2 targets have depleted all of their targets, we can shift them into this list. And so doing this efficiently will give you OM time per test case, and because the total sum of n is less than or equal to 300k, this will pass the last test data. And that is it for problem 2. Problem 3 should be presented by Danny.
Okay, hi everyone, I'm Danny. I'm going to be presenting the solution to problem 3, linguistics. So, in the problem, you get 2 integers and an m. For example, we'll take n equals 5, n equals 2. And you're given that there's an alphabet, and you're given a multi-set of letters from the alphabet. So, the multi-set A. As an example, we'll take like 1, 2, 2, 3, 4, and the rest will be 5. So importantly, the multiset is of size n times m, and the task, well, the premise is that you're going to make n words that are each of length m. So let's make spaces here. So these are each 5 words that we have on meta that are each of length 2. And then what we're going to do is we're going to store these words in a lexicographical order. So let's say S1 will be the minimum lexicographical order word among these 5 that we make, S2 and so on. Okay, and now our task is to answer for each k from 1 to n, what is the minimum that sk can possibly be independently. So like what's the minimum lexicographical string that we can get for sk, given that sk is a kth string in this sorted list of the words that we make. Okay, and so the idea is let's take k equals 4. So we want to minimize S4. We want to minimize the 4th smallest string in this list of 5 words. So ideally, we would just have S4 start with the letter 1, right? But the thing is, if we start with the letter 1, then there's only 2 ones. So at worst, like 2 of these strings can start with 1, which means that any string that starts with 1 is either the first or the second string. So S4 cannot start with 1. So what we have to do is go to the 4th which is this one, 2. So we want S4 to start with 2. That's the best possible. And then to fill in these so that they're all lesser e. So make S1 1, S2 1, S3 2, and S4 2. Okay, so now we have a way to make it to that S4 starts with 2. And then choose the second letter. So basically all of these are used. Now we have 3 and 4. And ideally we would use 3. But the thing is, if we use 3, then this string will actually be before this string in its graphical order. So that will make it S3, not S4. So we actually have to go like, we have to say that basically. And the important thing is like, these don't matter because these ones start with 1. Because they start with 1, they're already guaranteed to be lithograpically before these two. So we can just ignore these. But S3 starts with 2, just like S4 does. So we have to make sure that it actually does end up being before S4 in lithographical order. Which means that we have to choose this one as having 3, and this one having 4. Right, so the general solution is, if we're dealing with K, we have to sort our multiset of letters, and then assign the first K of the letters in the multiset to be the first letters of the first K strings here. So then that K letter will be the first letter of our string that we care about. And so then all the strings that start with that same letter are the ones that we have to worry about continuing for. So like, we start with like the first letter, we think as the K letter in the multiset A. Then we count and say that there's J strings that now have to start with the same letter. So now we could say that those other J minus 1, 2, 4 are SK, have the second letter be a letter that's before the second letter of SK. So essentially, looking at the letters after those first K letters, we have to assign the next J letters to be the second letters of these strings. So then the J letter of those letters will be the second letter in our string. And then we keep going like this. So we keep looking at how many strings, based on the letters that we've assigned so far, are equal to SK. And we have to make sure that, let's say that there's J at the current point in time, then we have to choose the next J letters to be the letters that we add to the strings. And we have to make sure that they end up being lexicographically less than our target string. Okay, and so that gives like a polynomial solution. So now to optimize this, what we want to do is first we sort our multiset A in sort of order, like this A is already sorted. And then we say for each distinct letter, we record the index that it starts. So like 1 this starts from 0 in sort of multiset, 2 position 2, 3 position 4, 4 position 5, and 5 position 6. And so now what we do is for each K that we're choosing as K for, we keep track of how many letters have we used, how many letters have we already assigned, and how many strings are still equal to the current SK that we have. So if we let the quantities be like A, or not A, let's call them X and Y. If we use X letters already, and we still have Y strings that are equal to our current value of SK, then we need to use the next Y letters to add to the strings. Which means that the next letter we add to SK will be the X plus Y letter in multiset A. And then now we have to update X and Y. So obviously, X will just become X plus Y, because we use Y new letters, and or Y. So we can just use this array we've made and check if these Y letters are all the same, then Y doesn't change. If some of them are different, then what we say is this letter, basically the ones that are still equal are the ones that we added this letter to. So the amount of ones that are equal to the current SK is the amount of letters equal to this other path. So it's basically just this is an x plus y minus the location in the array where that letter begins. So let's say like and by doing that, we can add each new letter in constant time. So pretty much the whole our algorithm is just takes linear time to length the output. And the bottleneck actually ends up being 4 anyways. So technically, you can say this is a nm log nm solution, so you can sort of you can use hand sort if you want, but really basically it's a linear solution. And that's problem C. So now for the next problem from the sample.
Problem D. Subarray majority. All the problem statements is that you're given string with 1, 2, 3 question mark. You want to fill in each question mark with numbers between 1 and 3, so that each subarray has a majority element defined as like half of the elements are equal to it, and it's half of the elements are equal to it. And the key observation here is that unfortunately, I just have to just obscure this immediately. No. Sacrifice you will make. The key observation. Suppose that the array has all of 1, 2, 3, because like if the array only contains like 1 and 2, say, then every subarray is going to have a majority. It's just going to be like whenever element that appears more in like array, either 1 or 2. So we only need to worry about like some arrays that have like all from those 3. Then any subarray with all of 1, 2, 3 must have the same majority. The proof. The rough idea is to shrink the array one element at a time.
Some trouble or a bit of both? I think it's hard to see.
each time we shrink the array, we delete one element from the subarray. And when we delete the subarray, as long as we still have all of 1, 2, and 3, like the majority element cannot actually change, because like to change an element, like you have to like make like one element appear like once you have to make like one element that usually appear less often appear more often than the other element. But then we're at the point where at the crossing point where the two elements have the same frequency, it's going to violate the majority condition. And therefore, like, this key observation is true. And then so firstly we can firstly it's easy to count. Arrays that have 2 or fewer distinct elements. These are not covered by the observation, but it's pretty easy to count them. Just like this, like some big CP, that just keep track of what elements that you use, and these majority conditions always satisfy these arrays. And for other arrays, this is like the main case. Assume that let's fix a majority of whole array of the entire array. And assume that is 1. Because like the 2 and 3 cases are like basically the same. What is this?
Don't erase the top one, just erase this.
Yeah.
Like I have to keep this thing visible.
Wait, should we use the sideboards if you can?
Yeah. Are they visible? Yeah.
They're
You can just search that.
And now we can like do now we can consider the following. Define a score of subarray to be the number of ones minus the number of 2's and 3's by this assumption and the key observation, any subarray with 3 distinct elements has non-negative score. And so we can do the following DP. Firstly, we store the current position. Like the current position, which is like the number of elements that you have already filled in an array. And the current score the score of the current prefix, sorry. So like if this is like m, then this is the score of the first m elements. For the position m, score in position M, then score of A1 dot dot AM. And then we also keep track of max score of A1 dot 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 AK, where A to AK plus 1 AM contains 2, and also the same thing, but with 3. So firstly, like, we have enough information for this DP because like when you're at the current position, you just to check the condition for all subarrays with 3 distinct elements. You just need to make sure that whatever like score of like the prefix that you before it that you're like subtracting out, that one like if it is far enough out to like contain like all of 1, 2, and 3, then like the score difference between like your current position and the previous position, it has to be a non-negative difference. And also like whenever we add an element afterwards, like, we can update the state. And this gives you an O of 1, 2, 4 dp for 70 points. And to get 100 points, you just need to make one change, which is like instead of like scoring these 3 values separately, you score, let's call this x, y, and v. For 100 points, we instead store x minus y and x minus v in the dp state. And like it turns out you can do that, just update these, and then that gives you an incubed dp for 100 points. So let's move on to the next problem. Yay! And we have our last problem, abelian, presenting irrational paths.
Hello everyone, I'll be presenting irrational paths.
Try to be a bit louder. I think it's hard to make a problem.
Also, like, write a bit bigger.
Yeah, right big if you can. The audio and video quality are not great. We apologize, audience.
Yes, so in this problem we have a directed graph, and we need to check if it is possible to make steps so that you create a irrational number using the edges on the path. The first thing we can notice is that if we have a graph, we can just reduce the problem to strongly connected components, because after making infinite number of steps, you'll end up in the, after making infinite number of steps, you're going to stay in the same strongly connected component after some amount of turns, because there are a finite number of strongly connected components. And if there exists a path that produces an irrational number in any of the strongly connected components that are reachable from 1, then you can just use that path. Otherwise, the answer would be no. So the first step is just to decompose the graph into strongly connected components, check the components that are reachable from node 1, and solve the problem for those components. And if the answer is yes for any one of them, then the answer is yes for the entire problem. So now let's assume we have a strongly connected component with nodes 1 to n. And we want to know if it is possible to produce an irrational path in that component of graph. Let's first assume it's not possible to have an irrational path, and every path is rational. It's not hard to check that all the paths that are rational, if there are multiple paths that are rational from the same node, then those paths produce the same exact number. assume we have a path that is rational. That means we can, assuming there are like multiple paths from the same node that are rational and produce a different value. Let's say this is like path 1, path A, and path B. At some point, you return to that node. You can return to that node. So, if there are multiple paths, path A and path B, that are different, that go back to the same node, you can do something like path A, path B, path A, path A, path B, and then path A, path A, path A, path B, and this will be an irrational number. So if there are two separate paths that loop to the same node, and none of them is a period of the other one, then there exists an irrational path. Which means that if there does not exist an irrational path, and every path is rational, then there is only a unique value you can get from starting from the same node. Yes. So now let's see that we can actually group the nodes into subsets in the SCC, so that, assuming we can only have rational paths, such that the nodes from the groups, all the edges in the strongly connected component are between the groups, and they form a cycle. This happens because if it was not the case, we could switch the, let's say we have, let's say our rational number is just just A1, A2, A3, A4, and AM periodically repeated. That means we have nodes from which we do the A1, and we step the A1 edge, and then there are nodes from which we step the A2 edge, and nodes from which we do the A3 edge, and we can group them, and that means we can actually group the SCC into groups, for which only the groups of with indices I and I plus 1 modulo M have nodes between them. So basically, we have groups 0, 1, 2, and M, and all the edges are written in groups like this. Assuming that the only paths are rational paths, and also edges like this. So, assuming such a grouping exists, how can we find the value of M? Let L be the group of be the subset of that node B is in. So for this node it will be 0, for this node it will be 1, for this node it will be 2. We know that L for any edge that goes from A to B, we know that LA is congruent to LA plus 1 is congruent to LB modulo M. For every edge that goes from A to B. So if we write this down for every edge and change the form of this to LA minus L sub B plus 1 is congruent to 0, but we will have a bunch of equations like this modulo M. So we will have LA1 minus LAB, 1 plus 1 is divisible by M, then LA2 minus L 1 is divisible by n, and so on. We also have this, that LB is congruent to dB modulo n, where dB is the distance from node 1 to B. Node 1 is just an arbitrary node. And if we calculate these distances and plug them in here, we'll have a bunch of numbers that are divisible by n. And if we calculate the GCD of those numbers, let that number be B, we can see that n should divide D. So n divides the GCD of all of these numbers, which is D. So if there exists a period like this, like if there exists a grouping like this, we found a number D, which is divisible by the number of groups that we have. So, first of all, if there are two nodes, B1 and B2, which have the same, which are in the same group, assuming they are D groups. So, oh, this is also a D. I'll just change it to R. So assuming there are two nodes which are in the same group, assuming there are D groups, and they have two edges that are not the same, that means they do not have the same digit on them. That means that it is impossible to create D groups like this. So if we have two nodes, let's just say, let's just assume there are like D groups here, and two nodes in the same group have outgoing edges with different values of them. So let's say this is like 1 and this is 2. That already violates our condition and means that we cannot have D groups. But this also works for every number divisible by that divides D. Because as we know, LB is congruent to RB modulo n. And if we change this model, and if this does not hold for modulo D, this won't hold for modulo n because n divides D. So if it is impossible to group our nodes to D groups, it is also impossible to group our nodes to n groups. However, if it is possible to group our nodes into D groups, that means by definition, by the thing that I just showed here, our graph is going to be periodic because we'll have D groups, and whatever we do, we're going to end up in the same period, and we're going to produce the same number all over every time we do these steps. So that would mean that the number we produce is going to be rational. So the algorithm is basically just calculating the distances from some node. For every edge, calculating this, finding the greatest common divisor, and checking if it is possible to group the elements by in D groups. If it is, then the answer is no for that component. If it is not, the answer is yes for that component. And we just calculate the order of all the components that are reachable from them. The total complexity is all of n in this solution. But that's the end of the review. Do you want to say anything?
Applause to Obedience for the amazing solution. Overall, thank you so much to all the presenters for bringing us the solution so quickly and thoroughly. It's really great spending your time on a Sunday afternoon with us. And also, just in general, a really big round of applause to our problem staff in general, who spent days and nights literally pulling all nighters, bringing you the problems that they are today. So, actually, they're living with us. So, It's time to turn the camera to our team. Say hi. And of course, we have the arts committee, the website committee, the logistics committee, who have all worked really, really hard to bring the contest today. So thank you guys once again for coming. It really means a lot to us. Your support allows us to do these really cool events and make these things happen. Without further ado, we'll be compiling the results about 2 hours and release the finalized results by 6 p.m. And then we'll try to contact the finalists and ask them about the eligibility by then. But before that, may you have a good rest of your day, and we'll get to you back soon. Thank you. Cool. Jover! Woo!